Welcome back to another lesson with me, Mr. Wong. We're going to go through the second part of the work done lesson, this time focusing on potential energy. Firstly, we need to define what potential energy is. If we use the context of gravitational potential, it is defined as the work that can be done on an object due to a gravitational force. If we look at how this is coincided in this diagram here, our object starts at a 0 point. So this is at a height 0. This is the reference point we're starting off with. We're saying the object is going to be pushed up or pulled up to a height h. Okay? And now we've got to try and establish the type of energy that would be forming due to this relationship. So what we know is work done is W equals Fs. When it comes to gravitational force, the force that's going to be exerted on this object at this very top point here is going to be Fg mg, mass times acceleration due to gravity. S, on the other hand, is going to be replaced with h. So instead of having a displacement, or the type of displacement we're looking at is a vertical displacement, so this becomes h, F becomes mg. So what we find is W equals Fg times S. We know that Fg is mg, so we substitute that in. We've included an additional point, and this point is called delta H. We have delta H here, and this represents the change in height. Okay? So when we go that through, so it's change in height. So if it's change in height, remember we started from a position of 0. So we went from 0 to some height called h. So what we're experiencing is a change in gravitational potential energy. And this is the formula we come up with. So this is the change in gravitational potential energy. Mass measured in kilograms. G, that's the acceleration due to gravity. So that's measured in meters per second squared. And here we have the change in height. So that's what potential energy or gravitational potential energy is how much energy change do we get when we lift an object from some reference point up or down. How much energy will we have stored and can be used by gravity to pull it down? So the formula we have here is Ug equals to mgh. Remember, this is the assumption that it's gravitational potential energy. If we want to look at the change in gravitational potential, you simply just change that over to mgh here. Okay, so nothing's too different between these equations. Again, energy is measured in joules. Mass is measured in kilograms because those are the appropriate SI units. Height is measured in meters. If we look at the reference point we have here, so let's say, where is the reference point? Because that's one of the questions people might ask. What if I change the reference point? Well, that doesn't really matter in our question for the change in GPE. Okay, so gravitational energy, if we're looking at the change in gravitational potential, okay, we're looking at the change in the height. So if we have this bit as our 0 point, and we looked all the way here, let's call this hi or h1, then the change in height is h1. Let's say we change the reference point. Let's say the reference point was down here, so this is our 0 point, but we only lifted our object from this point here all the way up. Okay, this might be the reference 0 point, but the actual change, the initial height, or the initial height here, moves to the final height here. So this is the only change we see. So this is our delta H here. So even if you have a question that says, oh, it's 30 centimeters, let's say it's 30 centimeters above the ground, and then it went to 50 centimeters, the only change, and it asks you what's the change in the gravitational potential, the only change in height you need to worry about, because it is asking you for the change in gravitational, is the 30 to the 50, which in this case would be 20 centimeters. So let's try some calculation questions here. Okay? So here are the calculations. I will move on in 2 seconds. So if you don't want any spoilers of how to do these, my suggestion is to to pause it right now. All right, moving on. Let's have a look at what we have in our question here. What can we do with the information provided to us? Okay, so let's firstly underline what the question's asking. We need to find the change in gravitational potential energy. Okay, so we're trying to find delta UG. So we need to know a couple of things. We need to know what the mass is. The mass, in this case, is 80 kilograms. What's the change in height? So from the floor of height 1.8 above the ground. So we've gone from our ground, which is 0, to 1.8. So the change in height we experience is equal to 1.8 meters. And then the last bit is, what is g? Okay, g is the acceleration due to gravity. So it's 9.8 ms squared. Some of you might be asking, oh, I've done some questions where g is negative value. Why don't we put a negative value here? The only reason being is because gravitational potential, in this case, is a scalar quantity, so we can write it as a positive value. The other point is the fact that our 0 point is here, and we're looking at how much gravitational potential has been gained. So if we're gaining gravitational potential energy, so if we're gaining gravitational potential, that means we see a positive relationship. So that's why we're going to leave g as a positive value in this case. There will be cases where delta G or delta UG will be negative, but we'll talk about that later when we talk about conservation of energy. So let's substitute this into our formula. And so we have mass equals to 80, G is 9.8, and then change in height is 1.8. I find that the final value is 1411.2 joules. Okay, remember joules is the units for energy. And so if I summarize that and find it to the closest 3 sig figs, I find it to be, if we go from here, be 1410 joules. If you want to make it into a smaller number, then you can divide it by 1,000 to convert it into kilojoules, which is what the answer we have here is, 1.41 kilojoules. In our next question, we have a 60 kilogram weightlifter that holds a 50 kilogram barbell 50 centimeters from the floor. Okay, so our initial height is actually 50 centimeters. Calculate the increase in gravitational potential, so we're trying to look for delta UG, after raising it to 90 centimeters. So it goes from 50 to 90 centimeters. So what's the increase we have? We have an increase of 40 centimeters. Remember, delta H needs to be measured in meters. So the final answer should be, or what I like to do, 40 times 10 to the minus 2 meters. Essentially, divide by 100. What about the mass? Is it going to be 60? Is it going to be 50? Or maybe both? So we need to look at what's actually gaining the gravitational potential. Our weightlifter is not moving, okay? He's the one holding it, or he or she is holding it down, and they hold the barbell up. So the barbell is the thing that's moving up. So this will be the mass we're looking at. So M is equal to 50 kilograms. If we have a situation where the weightlifter and the barbell was both lifted 40 centimeters, then you would add the two numbers together. But in this case, we're just looking at the barbell. Okay, let's substitute that in. So 50 kilograms, 9.8 again, and 40 times 10 to the minus 2. You get an answer of 196 joules. So that's the change in gravitational potential we have here. Move along to the next question. And we have a rock with 2,450 joules of potential energy at the top of a 25-meter high cliff. What is the mass of our rock? So what we're trying to find here is M. Okay. Question 9, we're also trying to find the change or the height we're at. So let's try and break it down. All right, so let's look at what we have in our numbers. We know that 2,450, that's our delta UG, joules. The height, so at a height of 25, so that is our H, 25 meters. We know that G is still 9.8 meters per second squared. So what is M? First things first, you got to substitute the numbers in. That's what they expect in the HSC physics. You substitute your numbers in, then you rearrange the equation. All right, so this is what we have. What we do next is to move the 9.8 and the 25 over to this side. And to do that, you divide both sides by those two numbers. And so you're left with 2,450 over 9.8 times 25. Substitute that in, and I'll find that the mass of my object is 10 kilograms. Going through to the next question, we have a 2.5 kilogram rock lifted from a height of 10 meters above ground. It gains 367.5 joules of gravitational potential. What is the new height? What is H? Okay, so 10 meters is our reference point here. So we're not going to actually use this in our question just yet, but we will get to it later. We need to firstly look at what the change in height is. We need to find the change in height. Then we'll find out what the final height will be. Okay, the mass is 2.5 kilograms. The change in gravitational potential energy is 367.5 joules. G is 9.8 meters per second squared. Let's have a look at the numbers. Again, substitute the numbers into the relevant equations first. Voila. Then you move it on to the other side. So we need to move 2.5 and 9.8 over to 367 by dividing. And so we find that the change in height is 15 meters. Okay. The question asks, what is the new height above the ground? So initially, we were already 10 meters above ground. We've changed and gone up by 15 meters. So our final answer if I just quickly erase what I just did here because I had the working out, is 25 meters. So the new height above ground is 25 meters. All right, so let's try and see how this all kind of comes together. So we know that the gravitational force is Fg equals to mg. What you see with the little arrows on top, these are just to represent that it's a vector. So just little vector arrows. We know that gravitational potential is related to the weight force. So this is how we showed it. Mg is equal to Fg. So we also know because we're bringing an object up, the work that we're actually doing, so this is work. So work is being done going up, and we're gaining gravitational potential energy. But essentially what's actually occurring is we're also doing, if we were doing the opposite and the object was falling down, okay, say the object is falling down now, we're losing gravitational potential, okay? And so in this case, the work that's being done would be negative because it's working with gravity. So what we could say is work done is the work done by gravity is considered a negative change in gravitational potential energy. So any work done by gravity, like I said, leads to a decrease in potential energy of our object. I'm going to finish it off here for today. We are going to look into conservation of energy using this simulation, but until then, stay safe and see you around soon.